This is the intuition video for question 1F on the 2011 MAT paper. In this question, we're given this horrible looking thing, x squared plus y squared plus 4x cos k plus 8y sin k plus 10 equals 0, where k is a parameter that varies between 0 and pi. And we're asked, for what k does this describe a circle? So in a minute we've got set k equal to 0, and we see that this equation doesn't describe any points. No x and y satisfy this. However, this isn't always the case. If we vary k, we'll see there's a circle appearing, moves and then disappears the other side. Now, why is that? Well, this horrible thing we can actually rearrange quite nicely, and as you'll see in the solution video, and we can get it to this form here. Now, the right hand side would, if this was a circle, represent the radius of the circle squared. So, as providing sine squared theta is big enough, i.e. that 12 sine squared theta minus 6 is greater than or equal to 0, we do in fact have a circle. When sine squared theta is too small, i.e. this value is negative, then we don't have a circle and we don't actually have any points to satisfy this, hence the empty graph that we get. So in the course of solving this question, we actually find that the range you get circles for is k or theta between pi over 4 and 3 pi over 4, but they're strict inequalities. So what actually happens when k equals pi over 4? Well, what happens is, essentially, you just get one point here, because the point minus 2 cos pi over 4 minus 4 sine pi over 4 does satisfy this equation. However, no other points do. So you don't get a circle, you just get a singular point, and similar happens for 3 pi over 4 on this side. There is actually one other really nice property of this problem, which is if we mark the centre of the circle with a green dot here, we can algebraically work that out to be minus 2 cos k minus 4 sin k. Then, as k varies, it actually traces out a very nice path, the centre. Because if we put in the ellipse 4x squared plus y squared equals 16, and vary k, you'll see the centre of the circle moves along the ellipse. And this isn't too unexpected with all the trigonometry and sine and cosine functions going on. And you can get algebraically to this by substituting in minus 2 cos k minus 4 sin k into this, and you'll see it is always a point on this ellipse.